factor into the context. And so this is actually a very nice kind of synergy between the events today. And I'm really very happy to give you, in my last hour or so of duty for the University of Hawaii, this talk. So let me start. And let me start at the beginning. And in the beginning, there was nothing. JD, can we switch the backlight off? Because, you know, astronomy happens at night and these pictures are all very dark. So, so in the beginning, oh, that's really dark. Okay. In the beginning, there was nothing. And this is almost biblical, but it turns out that our current cosmological understanding is actually very close to some of the creation mysteries of some of the religions. Like, for instance, right now, Buddhism has the head up because it is, and even the Hawaiian creation chant is basically creating the universe out of nothing. But even in the Christian religion, there is the idea of creatio ex nihilo, the creation out of nothing. But the difference is that nothing is completely different to anything that we can imagine. Nothing is actually the largest energy content of the universe. Most energy is in nothing, and everything else is just a very small perturbation of that. And let me try to motivate that with you. I think it's still a little bit too high. Some people complained that they can't see the down. Now we have to make a compromise between down and up. So what is nothing? Who of you have heard about quantum mechanics or quantum physics? Okay. And who knows that in quantum physics you cannot measure anything very accurately because there is a so-called uncertainty principle. So everything that you would like to measure in quantum physics has a little uncertainty associated with this. And this is not our ignorance or our inability to measure. It's a fundamental physical principle that nothing is really exact. And if you now apply this concept to nothing, which is kind of zero, when you say nothing is zero, if I make an experiment and I measure 0 1,000 times, I get always a different result. Sometimes a little bit more, sometimes a bit less. That means even nothing is uncertain. And this uncertainty is what we call quantum fluctuation. So every physical system that you try to measure has fluctuations. And physicists think about these fluctuations as little particles, pairs of particles, which are created out of nothing for a very short time, and then they annihilate each other and they give back the energy that they borrowed into nothing. And so whenever even if I take you out of the room and I take the chairs out and everything else, and then I pump down the room so the air is out, and then I cool down the surface of the wall so that the temperature, the waves are out, there is still something remaining, and that is this quantum fluctuations. And this idea of having particles where there is nothing is actually a very fundamental concept. And it turns out that the vacuum itself is actually much more complicated and much more powerful and energetic than we can even imagine. When you calculate the energy which is in these quantum fluctuations, the physicists, that's really embarrassing. There are 60 orders of magnitude uncertainty in what the energy of this quantum fluctuation field is. So we cannot really say this with very high accuracy, but we know that nothing is actually full of power. And it is so much full of power that you can actually create a whole universe out of that. And that is what I would like to motivate with you. By the way, if you have questions which are short, don't hesitate to raise your hand and I can try to explain it. We will have a possibility for some discussion afterwards. But just if something is completely inexplicable, then please raise your hand. So these virtual particles are everywhere, between you and me and in every other system they are existing. And now what happened in the beginning of the universe was that something which we still don't fully understand has actually ripped the universe apart. So a little piece of nothing, which basically was filled with quantum fluctuations, has been all of a sudden ripped apart and has become something of the size of a soccer ball. That was our baby universe. And what happened while the space was ripped apart was that these particles were ripped apart as well. So while before they were all close together, happy hand in hand, they created and they destroyed each other, all of a sudden you rip space apart and now there are the partners running around and they don't find anybody else to annihilate with. And so all of a sudden you pull real particles out of the vacuum of the universe and you create a universe which is filled with hot, real particles. And that is what we call the inflation in the beginning, in the first split second, 10 to the minus 32 seconds, something which was almost zero has been expanded into the size of a soccer ball. And this size of a soccer ball was extremely hot because all the energy that is in the quantum universe is all of a sudden running around as real particles. And when real particles are running around very fast, the temperature is high. And so the universe started with an extremely high temperature, something that we cannot really imagine, something like 10 to the 32, so 1 and 32 zeros degree Fahrenheit or Celsius, doesn't really matter at that scale. But okay, and from there on, what happened was that the universe, and this is something which is still not fully understood, why did this inflation all of a sudden stop? And why did it then go into a much more coasting, much more smooth increase in the size of the universe? So from there on, from this little inflation part, the universe basically expanded. And while it is expanding, it is also cooling down. Now, why does something that expands cool down? We know the opposite effect. When we are pumping up our bicycle, the tire and the pump gets hot because we are squeezing particles, gas, into a smaller volume. When we squeeze something into a smaller volume, it has to react with larger velocity, and the higher energy that is in there is actually transformed into heat. If you do the same thing, the opposite, if you take a bicycle tire and you inflate it infinitely, the gas in there gets colder and colder and colder. And all of a sudden, things are freezing out. So when it's getting colder, all of a sudden, other forces can take over. Like, for instance, if you have a lake in winter, which is filled with water, when it's getting colder, it turns into ice. And something similar happens with the universe. The universe, from this extremely hot early phase, freezes out into something where today we have galaxies and stars. And then we are sitting here in our galaxy on our planet, and we are looking onto the sky. But when we are looking onto the sky, we also look back in time, because everything that we are seeing somehow takes some time to get into our eyes. So when I see your faces, for instance, I see you all about a nanosecond younger than you are in reality. Because the light had to take some time from you to me. When we look at the sun, we see the sun about 8 minutes younger than it is. When we look at the next star, we see that star about 4 years younger than it is in reality, and so on. When we look at the next galaxy, it's about 170,000 years. And so we can actually, astronomy is something like a time machine where we look out in space and we also look back in time. And so we cannot look into the womb of our own mother, but we can look into the womb of another mother that lived there, and we can say what happened at that time, what did the first structures in the universe look like. And that makes astronomy so fascinating. Okay, now let's move on from here. And we say, we now know, and I don't have enough time to explain all of that. Actually, the story of the universe is so long, and I only have an hour, so I have to be selective what I tell you. So I cannot really touch on everything, but maybe in the discussion later. But through various different methods, we now know pretty well the cookbook, the recipe, what that puts together our universe. And let's start with what we know and love best. That is the heavy elements. Things that our Earth is made of, that we ourselves are made of, the carbon, oxygen, nitrogen, silicon, all the elements of the periodic table. You have a book there with the periodic table, right? And and all the elements which are heavier than hydrogen and helium. I don't need it. I just for him to look into it. All those elements actually are made in the belly of stars. So we are real stardust. I come back to that later because it's not quite true. Not all of our atoms come from stars, but in a sense, all the heavy elements, they are making only 0.03% of the total energy of the universe. So it's a minute factor that is actually making the world around us. Everything else is in other forms of matter and energy. I'm actually a specialist of black holes, or I love black holes and study them. And we have discovered that there are black holes everywhere. Every galaxy contains a central black hole, and I'm coming to that in the lecture. And how black holes are formed is a very important part. But the black holes themselves only make 0.001% of the universe, so they are also almost completely negligible. In the 20th century, a lot of elementary particles have been discovered, and in particular the so-called neutrinos have been discovered. Neutrinos are a sort of particle that doesn't interact with any other particle. This is basically a ghost particle that is, every second our body is crossed by millions of neutrinos and we don't even realize them. But we have learned in the meantime that neutrinos have a little bit of mass. And the mass of the neutrinos, we don't know it very accurately, but between 0.2 and 2% of the total mass energy of the universe is in neutrinos. And this is something which you could call dark matter, because they are existing, they are contributing mass, but they are not visible because they don't really interact with us. And therefore, these ghost particles, they contribute to the total physics and recipe of the universe. Now, all the stars, when we talk about astronomy, we talk about stars on the sky. The stars are the basic building blocks of our universe. But if you add all the mass of all the stars together, you only get 0.5% of the universe. So it's actually, the stars are almost like light bulbs that tell us where the other stuff is, but the light bulbs themselves weigh almost nothing compared to the rest of the universe. Yes, please. No, the stars are actually made out of hydrogen and helium, which was created in the Big Bang. And the stars themselves are making the heavy elements. So you see, the stars are 0.5%, the heavy elements are 0.03%, so the heavy elements are about 10% of the stars. So they are making the heavy elements. Yes, please.
Just going back to that, the first slide where you're showing that picture of the little pairs of molecules, where did you get that picture?
Yeah, the question was, where did I get that picture with the two molecules? Let me come back to you, and we can note that down, because that's a little bit too difficult for me to answer right now. Yeah? Okay, so we were already asking, what are the stars made of? The stars are made of hydrogen and helium, which were created in the first few minutes of the Big Bang. But most of the elements as we know and love them, and most of what is written in this chemical book with the periodic table of the elements, is actually still meandering around in free hydrogen and helium that was created in the Big Bang. And the stars are then forming from that hydrogen and helium, and they are then forming the heavy elements and so on. Yes, please.
What is the Big Bang?
Oh, I'm coming to that. So the Big Bang, I basically told you that there was this inflation where a little split second, a little piece of the universe was inflating to something like a soccer ball. And that energy will come to that. The Big Bang is actually not happening. The Big Bang has not happened. The Big Bang is still happening today. But that we have to come to that in a second. So the research for the last 10, 20 years or so has clearly shown us that there is much more dark matter than the pure neutrinos. There must be about 25% of all the matter in the universe must be dark matter. And physicists still don't have a clue of what that is. It could be tiny, tiny particles. It could be black holes. There are all kinds of theories, and we have not yet found the particle that makes the dark matter. But we find very, very strong and convincing evidence that dark matter is existing. And the dark matter is about 5 times more than all the normal matter. So you can regard ourselves, the normal matter, as a kind of perturbation or contamination of the universe. Most of it is made out of dark matter. And then even more is made out of dark energy. And this dark energy has turned out to be close to the energy of the vacuum. It is connected to the energy of nothingness. And so the idea is that if there is no universe, if this whole thing is gone, there is still dark energy. And that dark energy every once in a while can make a universe. And the universe is borrowing matter and energy and time from the vacuum. But in the end, as you will see, that universe will be gone and the vacuum will be left. Yes, you have a question.
Is that picture that you put for the black hole actually a picture of a black hole?
That's an artist's concept of a black hole. We'll come to that. We'll see that a little bit better. Okay. By the way, if you want, I can leave my slides here, and then you can look at them in more detail. Yeah, good. Okay. Now it turns out that in the last 10, 20, almost 30 years, computer simulations have become a huge and very powerful way of studying the universe. Because what you do is you assume a beginning, and you put in all the equations that you know, and then you let that universe evolve. And then we are sitting on the other side when the universe is already existing, and we are looking back in time and trying to see whether what we observe is kind of matching what we simulate. And so these computer simulations have become a very powerful way of interpreting the data that we are seeing. And so let me show you a computer simulation, what happens with this little soccer ball of hot matter that has been created in the original inflation. And the Big Bang is basically nothing else than the information that this ball has been expanding and has cooled down. And there is a simulation that we can look at that is basically this big ball is now flowing apart. And while the big ball is flowing apart, it is actually disrupting into smaller entities. And now the interesting thing comes. This movie, we'll have to look at this somewhat later. Let's look at it once more. While everything else is flying apart, when you look in detail at the centers where most of the matter is, they are actually not flying apart, they are coming together. They are flowing together. And this is actually, Woody Allen has already found that out. He says, the universe is expanding, and I still don't find a parking space in New York. And the reason for that is that New York is not expanding. And for instance, if I let this drop, that is also not flowing apart like the rest of the universe. It's actually pulled back by the Earth. So whenever gravity is actually stronger than the forces of the Big Bang pushing the universe apart, things are falling together. And that is how structure, large-scale structure, stars and galaxies are forming. Now this movie here is actually something that is completely forbidden because we are looking at our universe from outside. But we are in the universe, right? And so what we are seeing is not something that is expanding. We see everything around us expanding with us, so we don't really realize that the universe is expanding. And so this is reflected in this movie, which is actually the so-called co-moving observer. So that is somebody who is sitting in the universe and flying together with the expanding matter and sees what happens around him. And so we start out that movie with a basically completely isotropic distribution of matter, and then, like ghost hands, a structure is forming. We are seeing the same structure over here, but we see that the structure is actually forming a kind of cosmic web, so a web of filaments and deep voids, empty spaces. And the galaxies are like the chain of pearls are lined up on these filaments. And so in the large-scale universe, the universe is actually looking like a cheese, like a Swiss cheese, or like a sponge, or some kind of structure. Or maybe even some people think about brain synapses or so. So the universe is a big, large, very structured cosmic web. And in the center of these cosmic web filaments, that is where so-called clusters of galaxies are formed. So that is where galaxies are pulled in, and they are forming huge structures where there are about 100 or 1,000 galaxies on one spot. Okay, now we have to talk. So far we only talked about dark matter and about galaxies, but actually we know that galaxies are made out of stars. And so the stars are really the fundamental building blocks of our universe. And so what happens is when masses of gas are pulled together and are formed a kind of conglomerate of gas, it happens that in some areas this gas is becoming so clumpy and so turbulent that some pieces of that gas are actually collapsing, and they are forming a little ball of matter. And now the opposite of what we have seen before happens. That's the same effect as with the pump. When you pump up your bicycle, when you are collapsing a gas cloud, then it's getting hotter and hotter. And so inside these balls of gas, the temperature is so hot that the so-called nuclear fusion oven is starting to work. So in those stars, elements like hydrogen and helium, and then later carbon, oxygen, and so on, are burned. And the burning of this energy is actually enough to let those stars shine for about 10 billion years. And at the end of the lifetime of the star, basically all of that matter is burned, and there is a little heap of ash remaining, which is all these heavy elements that have been burned together and that are collected in the belly of the star. So in the end of the life, for instance, of the sun will turn into a red giant. It will blow up and almost swallow the Earth, not completely, but almost. And then at the end of that life of a star, the matter which is remaining is blown off in one of these beautiful smoke rings, which we call planetary nebulae. And then finally, what is remaining is this little heap of ash in the center of the star, which we call a white dwarf. It's a white star because it's a very hot temperature star, but it's a tiny, tiny star, so we call it a white dwarf. Now imagine such a white dwarf is roughly the size of the Earth, so roughly 12,000 kilometers in diameter, but it has almost the mass of the sun. So you have something which is extremely compact, a very heavy and compact form of matter. And those white dwarfs are more or less the end of the life, the graveyard of most of the stars that are in our galaxy will end up as white dwarfs. Yes, they have a huge gravity. They're very strong gravity because the more compact and dense something gets, the stronger is the gravity. I come to that point when we talk about neutron stars and black holes. I just want, yes?
How long do white dwarfs last?
Oh, white dwarfs can last. We come to that in a slide later. They can last for 10 to the 40 years. But I'll tell you what that is. So our sun has been born 4.65 billion years ago. So we are roughly at this stage here. And we know that our sun can still live another 5 to 6 billion years. So it's roughly at the half age. But what we also know is that the sun slowly, because there's more and more ash in the center, and in order to keep up the balance between the fight between gravity on one hand and the force that is pushing the star apart, the star has to expand, and it's getting slower and slower into this red giant phase. And that means that in the future, the sun will actually get hotter, continuously hotter. And we talk about global warming, which is a huge effect made by man. But ultimately, the sun will basically make the Earth so hot that the water starts boiling, and that at that time we have to look for another planet. And that is roughly here. So we are not too far away from that moment when right now it's kind of cozy and warm, but we are not too far away from the situation where the Earth is actually turning into something where we need a new planet. It's about 1 billion years. So for us, it's actually still a long time. So now let's look at stars which are more heavy than our sun. This is a star which is actually 10 solar masses, so it's 10 times as much mass as our sun. These stars are actually living a much more violent life. They are burning much faster, they are shining much brighter, they are huge stars. And such a star, instead of 10 billion years, only lives about 10 million years. And so within 10 million years, it is blowing away its gas. And in the end, no, it's not blowing away its gas. In the end, it's growing into a supergiant. And then in the end, there is a supernova explosion. And what was a white dwarf before is now turned into something which we call a neutron star. And the neutron star has roughly the mass of the sun. It's as heavy as the sun, but it is roughly the size of the Maui Valley. It's about maybe 10 kilometers in diameter. And so it is an extremely, extremely dense version of matter. This is basically the same density which is in the center of atoms, where the proton and the neutron are squeezed together. And such a neutron star, because we were asking about gravity, when you are sending a light ray around the sun, you know that the sun is slightly bending that light. Einstein has told us that the big masses are curving the space, and so that light ray is slightly bent. If you send a light ray around a neutron star, you're actually getting a bend which is almost 270 degrees. So the light is extremely strongly bent. And such a neutron star is almost a black hole, but not quite, because a black hole is defined as something where when you are sending light to that, the light is actually bent by 360 degrees and never comes back. And so a black hole is nothing else than a very condensed form of matter, which is so dense that light cannot escape anymore. Yes, please.
Does the light increase speed? Is the light constant? Or does it, when it goes around these turns, does it vary?
No, the light speed is constant, but the light frequency varies. So if you are living close to a neutron star, your clocks get much slower. Already here on Earth, the clocks are going a little bit slower than the clocks in the satellites. And when you're coming closer to a very, very heavy, very compact object, the clocks run slower. That is what Einstein told us. But the light speed is still the same. Okay. Yes, so the death of this star is what we call a supernova explosion. And that happens within a second roughly, within 1 to 2 seconds. That is when the stars are actually, in the end, the nucleus of the star is collapsing and turning into what we call a neutron star. And when the neutron star collapses to a black hole, that can go even faster. That can be in a millisecond or something like that. So it's a very, very fast event. And indeed, I will show you a few cases where neutron stars and black holes are formed. And this is some of the exciting research that we just got in the last few years. And actually some of it has been done here on Haleakala with pan-stars and other observations. So I wanted to, this is a whole set of maybe a week-long lecture to understand really the physics behind it. So we cannot really dwell into it too deeply. But I wanted just to introduce the terms white dwarf, neutron star, and black hole. And now we know that black holes are actually formed when stars which are even heavier, 30 solar masses and higher, when they end their life, what is remaining is so heavy and so compact that even the matter can no longer withstand the pressure of gravity, and ultimately gravity wins. I think in the universe gravity always wins, it's just a matter of time. Okay, so we have found in the last maybe 10, 20 years events which we can associate with the creation of a black hole inside a star. When you form a black hole in the inner of a star, the black hole can actually be so powerful that it disrupts the whole star. And then this ends up in a gamma ray burst where some flash on the sky is happening in a gamma ray burst. And this is an animation where a black hole has just been formed. These black holes, for some reason that we still don't fully understand, are able to form jets of matter, and they can eject jets of matter, and these jets can actually drill from the inside through the star, and this looks roughly like this. So the jets are kind of crashing through the star and then are eating the star from inside out. And in the end, what is remaining is basically a single lingering black hole, because that is what in the very, very center of the star has been formed. How the black holes are forming these jets is not fully understood yet, but it is very likely connected to magnetic fields. So the matter that swirls around the black hole is forming magnetic field lines. Similar to the sun, which is studied here in great detail, the sun is also forming magnetic fields. Sometimes these magnetic fields erupt and create solar storms. And something similar happens in this accretion disk around the black hole. These field lines are then, because of the rotation, they are wound up like, when you eat spaghetti in Italy, you use your fork, and then the spaghetti are kind of rolling up to the fork. That is exactly what happens here, but with much more energy. Yes, please.
How long does it take before it goes to that state?
So in the case of that heavy star, here this is about 10 billion years, so you don't worry about this. This is about 100 million years, and this is only about 3 million years. Now, this is still a huge amount of time. But the last stage is from here to here, maybe just a year, and the very last stage is only a second or something like that. So in the end, this explosion is going extremely fast. And those explosions are actually, all of a sudden you see a star, very bright star in the sky where there was no star before. That is what we call a supernova explosion. And those supernova explosions are studied here with pan-stars and others.
Like when it's a star, how long does it take until it gets to that stage? Like when the star is like big, and then how long does it take till it like eats it until it?
Oh, this event that I showed you here takes probably a few seconds. A few seconds, the black hole is eating its star from inside out, and that is what we are seeing as a gamma ray burst. So some flash of light somewhere on the sky is all of a sudden happened. We see such flashes every day, roughly once, and so we know that every day a new black hole is formed somewhere in the universe. Yes, please. This is a so-called Hollywood movie, so it's actually only an animation. It's not a real physical drawing. Yes, please.
The black hole is compressed matter.
Yes.
So it's not actually a hole. It's a black.
It's a black
Lump of
piece.
matter.
It's a black piece of space because nothing comes out. But in effect, it is basically very much squeezed matter. We don't really know what is inside the black hole because we cannot look inside. There are only theories. And Einstein has predicted that everything which is inside it actually falls into a so-called singularity and is in a single point with infinite density. But nature doesn't like infinity, so there are other theories who say that maybe you have heard something about string theory. Some people think that in the center of a black hole there is a spaghetti ball of strings, and these strings are kind of reaching out into the horizon of the black hole. So it's a much more complex. We just don't know. It's a matter of physics which is not yet completely finished. So now let me give you something. Let me show you something which has happened on 17th of August 2017, just a few months ago, and where here pan-stars and also our observers at the IFA had a huge role, namely the collision of two neutron stars. When you take two neutron stars, which each of them is about 10 kilometers of size, and you let them crash into each other, they are actually forming a black hole as well. And we have actually witnessed that for the first time in the universe, and that is a very important measurement. And so this actually is a movie that I would like to show you, which the New York Times has produced, and it is so great that I cannot narrate that better than they do. And so I just want, if you give me a few minutes of your time, I would like to show that movie.
130 million years ago, while dinosaurs still walked the Earth, a pair of dead stars collided. The explosion rattled space-time and sent waves of light across the universe. On August 17, 2017, light from that explosion appeared as a bright pinprick in the galaxy NGC 4993, and then faded to a glowing red ember. Ripples of traumatized space-time from the distant explosion squeezed and stretched the L-shaped arms of the LIGO and Virgo gravitational wave detectors. Converted to sound waves, the ripples produced a faint rising chirp. 2 seconds later, NASA's Fermi Space Telescope detected a gamma ray burst, a brief glint of high-energy radiation from one of the most violent events in nature. Astronomers scrambled to point their telescopes before the precious light faded away. First on the scene was the SCOPE telescope in Chile. Right on its heels was the nearby Dark Energy camera. Antennas of a very large array strained to record radio emissions from the fireball. Even the Hubble Space Telescope turned its peerless mirror toward NGC 4993. Within hours, the distant explosion had become one of the most observed events in recent astronomical history. Astronomers think the story began with a pair of massive stars that were orbiting each other. The larger star ran out of fuel and collapsed into a dense neutron star.
Like I told you.
Neutron stars are the densest visible objects in the universe, spinning dervishes bristling with powerful magnetic fields. A teaspoonful of this star stuff would weigh as much as Mount Everest. The intense gravity of the neutron star began to steal gas from its aging sister star. The swirl of hot gas dragged the two stars together until the neutron star began orbiting inside its sister, shredding its outer layers into a swirling cloud. But the sister star survived this meteor and eventually exploded too, collapsing into a second neutron star. The fuse was now lit. Twin spheres of incredible density were now locked in an ever-tightening dance of doom. Shedding energy in the form of gravitational waves, the two neutron stars spiraled closer and closer, faster and faster, and finally merged in a moment of astrophysical ecstasy. A kilonova explosion, a crucible of cosmic alchemy. The swirling cloud of superheated atoms was bombarded with neutrons, forging new atoms of gold and platinum and other heavy elements. Scientists think that most of the precious metals in the universe were created in kilonova explosions like these. When black holes collide, there's nothing to see. The LIGO can hear the chirp from the gravitational waves. The neutron stars are visible matter and collide within a glowing cloud. This was the first gravitational wave catastrophe that astronomers saw as well as heard. Our first glimpse of the mysterious physics inside neutron stars, and the first fleeting glimpse of a cosmic mint in the sky.
Wow, yeah. So this discovery was actually followed by about 4,000 astronomers. There probably are on the order of 10,000 PhD astronomers in the world, and almost half of them were following that up and were publishing papers about it. And we here at IFA, both in Maui and also in Manoa and on the Big Island, we were extremely lucky and fortunate because we were in the front seat of this discovery. And the reason for that was that our new faculty member that just started in August, Benjamin Schappi, was actually among the discovery team that has seen the optical counterpart for the first time in Chile with the SWOPE telescope. And a week later, or 2 weeks later, he became our faculty member and he brought a pot of gold with him. And so that was really a huge success. And so some of the pictures that you have seen are basically this galaxy before the star exploded and then after the star exploded. And then our own beloved Pan-STARRS telescope, with in particular Ken Chambers and Eugene Manier. Pan-STARRS has the most beautiful and deepest images of the whole sky. And so they could actually very accurately see what was there before and what was there afterwards. And they could find out that this object has done something that no object ever before. It was skyrocketing down, it became bright, and a few hours later it was already much, much dimmer, and no other objects, or no other explosion of this kind is doing that. Normal supernova explosion, they take about 2 weeks or so to rise and go down. This was gone within a few hours, and so Pan-STARRS played a huge role in alerting all the other astronomers to say, look here, this is really something very special. And so we had really our seat in the forefront. And imagine this event has to rewrite the textbooks. So when I told you we are all stardust, this is only partially true because only the light elements in the periodic table of the elements are actually made in stars. The heavier elements like silver, platinum, gold, but even iodine. You know, our body needs a lot of iodine to feel healthy. That iodine is produced in neutron star mergers. So we are not only stardust, we are also neutron stardust. And that was a huge revelation, and which also had a significant effect from here. And by the way, you know, a lot of the mass of our body is made out of water. And, you know, water is, the chemical formula is H2O, so it has 2 hydrogen atoms and 1 oxygen atom. The 2 hydrogen atoms in water are coming directly from the Big Bang, and the oxygen comes from a stardust. So we are not completely stardust, we are also Big Bang dust. Okay. So now this brings me to a little side effect, because our Pan-STARRS telescope is not only detecting kilonova, it is actually mainly there to find so-called killer asteroids, asteroids that are posing a potential hazard to the Earth. But Pan-STARRS has also done the largest and biggest all-sky survey that has ever been done. And the sky has now been observed about 120 times all over. And so this is a complete change of how astronomy is done. And Pan-STARRS has been originally evolved and developed by Nick Kaiser, our faculty member, who has in the meantime taken up a professorship in Paris. And then Ken Chambers, Jean Manier, and a whole team of astronomers in particular also here. They are right now, while I'm talking, they are observing up there in the first floor and do the next discoveries. And the Pan-STARRS data has been made public to the public. Yes, please. This one, yeah, that is the Pan-STARRS telescope. This telescope is sitting on the top of Haleakala. In the meantime, we actually have two telescopes. The second one will open its eyes soon. I was hoping that I can get the first picture before I leave, and the clock is ticking, but the eyes will open very soon. Here you see a beautiful picture where in the background you see Mauna Kea, taken from Haleakala. And this is the sky as observed with Pan-STARRS. So you see the Milky Way here. When you look in detail, you see constellations like Orion, Scorpion, and so on. So you get basically the whole sky in a pack. And the data that is there is about 4 petabytes. I don't know whether you ever have heard about petabytes. Maybe you've heard about terabytes, because the biggest disk, I come to you in a second, the biggest disk that you can buy, maybe about 10 terabytes. This is about 400 times more. And this data is now served to the public, so every one of you and everybody else on the Earth can actually dial in to the Space Telescope in Baltimore. And the Pan-STARRS archive in the Space Telescope is very popular. This is the Hubble data which has been served. This is the Pan-STARRS data that has been served. And the Library of Congress is about that size. So the Pan-STARRS data has already been served more often, I mean more data than the Library of Congress. But if you add all the data together, 4 petabyte, that is about 400 times the Library of Congress that we have there. So now please your question. Oh, this year. Yeah, that is one of the nebulae in the galaxy. We will come to that. We'll see that later a little bit in greater detail. Okay, so what I wanted to show you that Pan-STARRS in October has made a discovery that was really mind-boggling. And I don't know whether you have ever heard about Oumuamua. Do you know what Oumuamua is? Let me skip over that for the moment. That is just a number of potentially dangerous asteroids that Pan-STARRS and also Atlas have found on Mauna Kea. On Haleakala, compared to all the other telescopes. But Oumuamua is this guy. Have you seen that? Yes. Almost everybody has seen it because it has become such a huge press. Pan-STARRS at some point has discovered an asteroid which does not belong to our own solar system. Everybody else is kind of flying around the sun, and they have found an interstellar visitor, somebody who came from another star and visited us, and it's already gone now. But through observations, through many telescopes, I mean, Haleakala has discovered it, but then it was observed from Chile, VLT of ESO, Gemini South, then also Gemini North has picked it up, the Keck telescope has picked it up, Canada, France, Hawaii, and the UCART telescope, and UCART is now our own telescope. We have made this, and you see that the light curve of this object, that means the brightness, has changed dramatically and has this regular dips. And the interpretation is that this object is actually rotating, and it is actually a large cigar-shaped object. And here we see how it is flying. This is 2016. At the end of 2016, it was passing by Jupiter. It was passing by the inner planets. It was passing by Earth and Venus and Mercury. And it was coming relatively close to the sun. And if it would be a comet, then it should have developed a big tail, but it didn't develop a big tail. So it was already on its way out again when we have discovered it. So we only had a very short period of time, because it's traveling very fast, where we could study it. And the conclusion is that this is not only the first interstellar visitor, but also it has a very, very funny shape. Nobody really understands how you can make such a cigar-like thing. So, and then what is unfortunately not quite true, the surface is not silvery shiny like this. The surface is more red. It seems to be covered with biological, or with how they are called, organic molecules. So it could be that this is a visitor from outer space, from another solar system. And I actually believe that on such objects, it could very well be that the building blocks of life for other stars have actually been preserved and are spread around the galaxy. And so this could very well, objects like this could have a very big impact on life on other planets and other solar systems. And no, this is an artist's concept, because the only thing that the photograph would only be a point, a little bright dot. And the only thing that we know about it is this light curve. And in the meantime, this was at the end of, I think, November. In the meantime, you see here, 27th of October. This was actually at the end of October. In the meantime, that object has been observed by the Hubble Space Telescope and by other telescopes. And I was told by Karen Weech that the orbit looks very interesting. She doesn't say what interesting means, but obviously there are still some mysteries associated with that object. Some people speculate that it might be an artificial object, like a spacecraft. It looks very similar to the monolith in the Odyssey 2001. And so we really don't know yet. But what we know is if this is a natural object and not a man or an alien-made spaceship, if it is a natural object, then there should be one every year roughly coming by. So next year we might expect another one, and now our eyes are very sensitive to that, and we will then hopefully discover that before. No, it's not in orbit. This one is gone by far, but a new one. We have calculated the likelihood of finding something in a short period of time in our solar system. And then you can also, it's only one, so there's a huge error associated with that. But people believe that at any moment there are about 25,000 objects like this in our solar system. And only we haven't seen them yet. But now our eyes have actually been alarmed, and now we will see them. And there have even been ideas of building a spacecraft by NASA and following one of these guys, maybe even landing on one of them. So we are opening a whole new can of worms here. Please. Oh yes, that's a huge, important question. It's about 4 football fields long. It's about 400 meters, and it's about a tenth of the size, so half a football field wide. So it's not very big for a cosmic object, but it would be sufficient. If it would, for instance, fall down on the Earth, it would make a huge crater here, and would probably also affect some life forms on Earth. Yes, please. No, I think it. People believe that these could be, like, carbon is producing carbon chains. You know that carbon is also producing these fullerenes, these buckyballs of. So carbon has actually the capability to make very complex organic chemistry, benzol rings and things like that. And they believe that this object has been at least 200 million years on its way. And so the cosmic ray radiation, the energy which is out there, has slowly transformed it into a kind of dirty brownish surface. But it could be ice below that surface, it could be something else below the surface. And we still don't quite understand, because it is rotating every 7 hours. So it's a pretty large rotation for such a 400 meter object. It has to be relatively solid, otherwise it would have already flown apart. So it must be rock or frozen ice or something like that in there. Okay.
What is that big beam of light?
Oh, that's just the sun. I think that's the sun that illuminates it so that we can see it. And you?
How do you know that it's a flat?
Yeah, so you can assume if you take a ball, for instance, a normal round ball, and you let it rotate, then from every direction it looks the same. So wherever you look at, it would roughly look the same, and therefore you would see something which is absolutely flat here. If you take an object like that, and let's look at the movie again, then sometimes in this movie it appears dark, and sometimes it appears bright. So when we are looking at the small side, then it's appearing dark, and when we are looking at the bright side, it appears brighter. And that would create this kind of very strongly variable light curve. Okay, let's, just for a little bit of proudness, about 2,000 pieces of press coverage came through that discovery. Most of the global large media have covered that, and it is, I think, one of the most important discoveries of at least of the last year. Now imagine we had, yes? It is faster than man-made spaceships could travel. But I think with new motors, like for instance hydroelectric motors, and we have specialists here in the audience about new types of thrusters, it might be possible to reach something like that. There is also the idea of Stephen Hawking and others to create something, a little spacecraft which is not bigger than an iPhone, which is actually covered. Oh, what's that?
Comet from Deep Impact.
Oh, okay. Well, that's actually a good idea. Yeah. So let me just finish that question. So modern spaceships could, in principle, be able to reach it, but not our current fleet of spaceships. So I think we need probably another 10, 20 years to develop something that could reach that. JD has just given me another model of another asteroid, which is actually a comet, and that is the comet that the spacecraft Deep Impact has hit. And now imagine this is rotating, and sometimes you see the small side and sometimes you see the big side. Then you also see a modulation of that rotation, and that is what we see with this object. Yes, please.
So if it's rotating like that, if you land a spacecraft and it wouldn't the spacecraft fall off?
Yeah, that's actually so the question is, if it is rotating so fast and there would be people inside, wouldn't they fall off?
Or the spaceship would like fall off and go flying because it's gonna be upside down.
Yeah, that doesn't matter. No. You know, the Earth is rotating as well, and we don't fall down. So I think rotation itself is not such a big problem. Okay, I'm taking much too long to get you to the end of the universe, so I think I have to. I think I have to skip over a few things, but I want at least now I'm going back out to very large distances, to galaxies in the universe, and I want to show you another very important piece of discovery that has been made in our institute by Brent Tully and others. This is a simulation of how our local universe should look like. And you remember I talked about these filaments and the voids in between. This is a very realistic simulation where we are basically here, we are in a kind of suburb of a big city. And this big city is called the local supercluster. And the largest object in that local supercluster is the Virgo cluster. So when you look here, this is the local group where we are living. And the Virgo cluster, which is a cluster of galaxies in the direction of the constellation Virgo, is the closest big city that we could travel to. I mean, if we would fly faster than the speed of light. So it's our local universe. And Brent Tully, our good colleague at IFA, has for many years and decades developed a method where he can actually measure very accurately the distance to other galaxies, and he can put the galaxies into a three-dimensional picture. And now I would like to invite you into a journey of the universe where we are flying basically from here to there, and I just want to give you a feeling what that looks like. And so this is also coming with music. Who of you knows the sky? And who knows what constellation this is? Yes, it's Orion. So it's the Hunter. There are the three belt stars, there is the sword, there are the knees, and so on. And so now this becomes live, and we are flying into the direction of the Orion. And here is the Orion Nebula. Where's the music? Oh, yeah. We are still in our own galaxy. The Cat's Eye Nebula, you're right, that was wrong. This is the Crab Nebula. And this is our own galactic center. Now we leave our galaxy. That's our galaxy. We see the Magellanic Clouds and other clouds around us. And now we visit the Andromeda Nebula and M33. Okay. So how did Richard Strauss know how long that journey would take? Every picture that you see here is a real picture from the Hubble Space Telescope of a real galaxy. So this was not a Hollywood movie, that was the real sky. And Brent Tully has put them together in the right three-dimensional scope. And you saw that when we approached the cluster, the sky was not filled with galaxies completely, but we were kind of traveling along a road or a village into the big city. And this galaxy is actually 1,000 times bigger than our own galaxy. And that galaxy has a black hole in its center, which is also 1,000 times bigger than the black hole in the galaxy. Now, I think I cannot in detail talk about black holes here because we are just running out of time, but I would at least like to show you. Our own black hole in our galaxy has 4 million solar masses. This one has about 4 billion solar masses, so about 1,000 times more. And you know that our whole galaxy has about 100 billion stars. So this thing is still a very small fraction of a whole galaxy. But that galaxy probably has 1,000 times more stars than our own galaxy. And the reason for that is it is sitting in the middle of this cluster, and the other galaxies are coming by, and they are eating. So this galaxy sits like the spider in the web, and it's eating other galaxies, and it's filling itself up, and the black hole is eating and getting bigger and bigger. And so that's how we believe that the universe... at the end, I will show you a movie that kind of is our current understanding of how the universe evolves on large scales. Yes? Stacking? Oh, sucking. Yes, this big galaxy is actually... Yes, the question was, is this galaxy sucking up other galaxies? Yes, it does. And because gravity wins. Gravity is pulling them in. This has a huge amount of gravity, and it can... Yes, yes, indeed. So why don't I jump to this thing immediately? I'll just skip through a few very important pieces. I just show you some observations from Mauna Kea, but I will actually skip over to first. This is the object that we have just visited, the M87. This is this big object. It has in the center a black hole. And you were asking, how does a black hole look like? So it's actually black. No, so the matter before it falls into the black hole starts to heat up and gets very, very hot, and therefore a black hole looks like a ring of hot matter. The black hole itself is black, but the stuff that swirls around it looks bright, and that's how we believe we can detect black holes. Now I'm coming to the question, what happens when two galaxies are colliding and when they are actually kind of swallowing each other? Some people call this galactic cannibalism because one galaxy eats another, but on the other hand, the other eats the other as well. So both of them eat. So I call it a galactic marriage. So two galaxies marry each other and they become something even nicer and bigger. And that is caught here in the action by a beautiful picture of the Hubble Space Telescope. But we can also simulate this. I'll skip over this because that is some X-ray observations. But we can simulate the merger of two of these galaxies. And then we can also see that the two black holes are merging, as we have seen in this movie. But let me show you a simulation which is very detailed, where a computer now has been asked to basically tell us how exactly the merging of two galaxies happens. And so this computer simulation is basically running. You can see the clock here in million years. So we are at 200 million years. The two galaxies are crashing into each other, and they kind of rip each other apart. And so the galaxies are turning into a big mess, like a train wreck. And then these two galaxies, you can still see them, but it takes about a few 100 million years. Then they crash into each other again. And when they do this, they merge into a single bigger galaxy. And now the black holes in the center are actually starting to activate, and they are actually doing a lot of mess, and they are blowing out a lot of the gas. But the stars of these two galaxies turn into something which we call an elliptical galaxy. So the two spiral galaxies that were crashing into each other are turning into a round elliptical galaxy. And that is how we believe that the life of galaxies is evolving. So basically you start with two galaxies, they crash into each other, a lot of things happen inside, the black holes are starting to become happy and eat a lot, and they get fatter and fatter. At the end, the black hole is getting the brightest object of the whole thing. That is what we call a quasar. And then when the quasar is kind of dying out because it doesn't get enough to eat anymore, then you have a kind of round elliptical galaxy, which is indicated here in this blue light. But in this case, this galaxy is famous. It's called the Sombrero Galaxy because it looks like a sombrero. The Sombrero Galaxy has already started to build up another disk around itself. And so that Sombrero Galaxy will turn later into something like this, which has a big blob in the side, which is the elliptical galaxy, and then it has the rings around. And so I would like, before I leave you, I would like to show you a simulation which is now the most detailed simulation of the current time, where we start out basically with specks of gas in the early universe. And this gas and dark matter and everything is collapsing into these filaments and into the voids. And as soon these filaments are starting to produce stars. So the blue light is the dark matter, and the red light is the stars, which we are seeing. And the stars is the only thing that we are seeing shining. We cannot see the dark matter, so we can only see these bright lights like beacons, like lighthouses, telling us where the dark matter lies. And this becomes more and more detailed. In the centers of these galaxies, the stars are forming, black holes are forming. The black holes are starting to make a lot of mess in the center of the galaxies. And that is actually creating here kind of explosions of matter. Supernova explosions are pushing out the heavy elements that are created. And slowly the whole universe is polluted with stardust, with stuff that is produced in the center of stars. And this is indicated here. The green material is still old material, and the blue is a little bit younger, and the red is the youngest material, which has the highest chemical enrichment. And there are basically, the universe on that scale is like a fireworks at midnight at New Year's Eve, because a lot of things are happening all over the place simultaneously. And our galaxy is just one of these, sitting in this whole kind of cosmic web that lives for a very, very long time. And so that brings me to the end of the talk. And now I have told you so much about the universe, and you probably have forgotten what I said at the beginning, and therefore I tell you the whole thing again. But I tell it to you in a very condensed time scale. So what I did is, I have created the so-called the calendar of the universe. The Big Bang starts on 1st of January. You can't read that very well, but the Big Bang starts on 1st of January in the last year. And today we are basically at the New Year's Eve of the new year. And so now I have compressed the whole life of the universe into 1 year, and that is what I call the calendar of the universe. So about 14 minutes after midnight, the universe became so cold that it basically became visible. We have skipped over that part. The first stars that we were already the first stars that were forming in the universe formed about 5th of January. And those stars very likely also produced the very first black holes, because those stars were very heavy, and so the end of a star is a black hole. The stars then are starting to create the elements. Nothing was there before. Everything had to be formed. And so carbon, nitrogen, oxygen, everything we know and love and eat has been prepared by stars for us. Let me finish, and then maybe you can. No, why don't I ask a question? Because it's too long. What's the question?
Is that October the one with the K October?
Yes, sorry, that's a German. That's a German biograph. Good catch. We'll come to October. Sorry. The very oldest galaxy from which we have received light has emitted its light on 13th of January. So that's how far we can actually go back. But this was a very bright and luminous galaxy, so the fainter galaxies, we cannot look that far back. And so we need the next generation of telescopes, the James Webb Space Telescope and also the 30-meter telescope, to really dig into this early time when we can see the first stars. On 27th of March, that was when in the simulation everything started to cook and boil. That is what we call the big feast, because the quasars were, the black holes and the galaxies were actually happily merging and eating each other, and so that was the big feast. Then there is actually a very long period of time where nothing happens apart from stars are forming, are dying, are producing more heavy elements, until there are so many heavy elements that you can form a whole planet out of heavy elements. And that is when the sun and the earth formed. Because in order to form something like the earth, you need a lot of heavy elements. You need silicon and whatever is in the earth and core, and you need iron and so on. And it turns out that this took about 9 months or 8 months roughly before that could actually happen. Now astronomy stops, and I turn to biology. Because already 3 weeks later, so you see this took 6 months, and 3 weeks later the first life forms were existing on the Earth. And the first life forms were single-cell bacteria, but they already had DNA and everything. They had the whole gene technology to replicate themselves and so on. The hugely complex mechanisms and organisms were formed within 3 weeks of the cosmic life. I believe this is impossible on Earth. I mean, I'm not a biologist, but I think this is just a very, very short time. And that makes me believe that the building blocks of life, the Lego blocks, have actually rained down on the Earth from other stars, which already had them ready-made, through objects like Oumuamua or maybe others that come from other solar systems and bring us the life forms. So this is what is called the panspermia theory. So the spermia of life maybe already existing elsewhere, and they rain down. But that's my personal opinion. That is by far not shared by all my colleagues. That's just how I see things. So now something else happens. You wait for another 3 months between 28th of September and then mid of December before the single-cell bacteria, the very simple mechanisms, turn into much more complicated things, like vertebrates and plants. Within 3 days around December, there was what we call the Big Bang of evolution. All the building blocks of today's plants and animals were already formed at that time, vertebrates and plants. And so it's another mystery how within 3 days, I mean, you wait for months here, and within 3 days, all of a sudden, you have all the evolution happening. Okay, then around Christmas, the trees were ready. So December 24th, you get forest, fish, reptiles. And the reptiles were actually also the dinosaurs, right? So the dinosaurs were created roughly around Christmas. Oumuamua started its journey on 25th of December. So 200 million years ago, we don't know exactly how old it is, but that's just a rough guess that Oumuamua was formed roughly at that time. And also, by the way, the first mammals were formed. So the little rodents and so on, the rabbits, they formed roughly at that time. But at that time, the dinosaurs were still dominating the Earth. The neutron star merger that we saw, the kilonova, emitted its light on 27th of December. This object is also roughly 170 million light years away from us. So it took 170 million years for the light to get to us. And that was roughly on 27th of December. Just to give you a perspective. So Oumuamua and that neutron star merger are almost on the same day. On 28th of December, the dinosaurs got extinct. Oops, there was an asteroid that hit the Earth or some other cosmic catastrophe, which made not just the dinosaurs extinct, but also a lot of other life forms. I think 30 or 40% of all life forms died at that event. Okay, then on basically prime time on New Year's Eve, at 8 o'clock in the evening, the first hominids start to appear. And those were the things that were still not, they were still crawling, and then they slowly opened up the Australopithecus and all of our forefathers. 83 minutes before midnight, Haleakala was formed. So all the Hawaiian island chain is only the last hours or so in the life of the universe. Our modern humans, the Homo sapiens sapiens, was formed about 6 minutes before midnight. At that time, this Homo sapiens still lived with other humanids, in particular the Neanderthal man. And you know, the Neanderthal man then got extinct roughly 70 seconds before midnight. But we now know today that the Homo sapiens and the Neanderthal man actually crossbreeded, and they actually fell in love to each other. Because we could analyze teeth of humans, and we saw saliva of Neanderthal men and human teeth. And so they must have kissed each other. But unfortunately, Neanderthal man died out. And then 4.6 seconds before midnight, Jesus Christ was born. That means our modern time started. But to be fair, I mean, all world religions, whether it's Buddhism, Judaism, and so on, were formed in the last 10 seconds of the universe. 0.23 seconds, the blink of an eye, is our own life in this scale, because about 100 years, all of us will get 100 years old. This is roughly 0.23 seconds. And so now we are on the current time, on December, and now we can look a little bit in the future. The gravitational waves from this merger that I showed you, where two galaxies were joining each other, will reach us roughly on 3rd of January. I hope that Pan-STARRS is ready by that time. Sorry, no. We will be ready tomorrow. And then on 22nd of February happens what I told you. The Earth is getting too hot to live on because the sun is slowly growing. The water will start to boil on Earth. And that is the last moment when we have to travel to another planet. By that time, Mars is getting relatively cozy. Mars is relatively cold still, but the sun is getting warmer and warmer, so Mars will be habitable for quite some time. So we might be able to hop to Mars. But the latest, when the sun is really turning into a red giant, we have to turn to another planet. And if we find another planet, then on 16th of April, we can actually... we can see the merger between the Andromeda Nebula and our own galaxy. So our own galaxy and the neighbor galaxy Andromeda Nebula will go into a big dance and do exactly the same that we have seen there. But that's not the end of the story. It goes on almost infinitely, and that is the unimaginable fate of the future of the universe. So we started out with the Big Bang, with the inflation. The universe cooled down. This was the time when the universe was cold enough that we could actually see it for the first time. And these are the dark ages where TMT hopefully can shed some light in, where the very first stars are formed, and then the stars form the galaxies, and we are here today. Now this is at 10 to the 10 years, so it's 10 billion years. That's a 1 with 10 zeros. Now this scale is really crazy. This is another 10 billion times more than 10 billion years. So this is actually 10 to the 20 years, 10 to the 30, 40, 50, 60, 70, 100. So it's unimaginably long. And what happens is the universe will expand, continue to expand, but we know today that the universe is expanding in an accelerated fashion. So that means the galaxies are flying apart tomorrow faster than they do today. And that means you were asking, what is the Big Bang? The Big Bang is still happening today. The force that is pushing the galaxies apart is still active today, and it's accelerating the galaxies. And that means that the universe, everything will flow apart much, much longer. At some point, the white dwarfs will die, the protons will decay, and the only thing that will remain for a very, very long time is the black holes, because the black holes are the longest lived life form that we know, at least in our universe. But we know from Stephen Hawking that at some point even the black holes will dissipate and re-radiate. And so the universe starts with nothing and it ends with nothing. And it's just a phase in the life of something bigger, which we call the multiverse. But it's a very, very interesting and long phase, and we still don't understand all of it. So I thank you very much. Mahalo. Okay, maybe we can turn the light on a bit, and then if there have been wonderful questions, and in particular you kids have asked really great questions, and there's one more here, and then two more. Yes. So the question was, did I hear about the theory of multiple universes? And what are the odds that this is realistic and that it's really true? Okay, first I have to say we are touching an area of physics where we almost know nothing about. But still, what we know is that our universe was created out of almost nothing, and it was exploding. And this is actually consistent with the so-called chaotic inflation, where this doesn't happen just once, but it happens all the time. So while we were talking, maybe there were already 2 universes that were created between you and me. But not all of these universes are so lucky as ours. Most of them are basically dying immediately because they're either too wimpy or too big, and they are basically exploding while we don't even see them. So we still haven't found out why a universe is so long-lived as ours. But this picture is basically bringing us to the picture of the multiverse, where you think about a hot boiling water pot. When you have boiling water, there are little bubbles that are coming up in the water. And these bubbles, everyone is a universe. And so in this picture, we are living in a hot boiling bubble, which is the vacuum, the energy of nothingness. And that every once in a while is creating a bubble, which is a universe. And some of them are lucky so that they can actually survive. But when you ask, I mean, what we are seeing of the universe is only a tiny speck. It's almost like the tip of a needle compared to the whole Earth. So our universe is really much, much bigger than what we can see of it. And that means that the multiverse must be even much, much bigger than that. So it's so mind-boggling big that we don't even know about how to explain it. Okay, so we have 2. Yes, so what are the theories why Oumuamua is not spherical? I mean, how could you create in a natural way such an object? I believe it had to be connected to some violent event. So for instance, if you think about a supernova explosion, or if you think about a neutron star merger, there might be matter which is expelled in a liquid form. And that matter, when it then cools down, could freeze and turn into something like a linear shape, and that could also give it the rotation and everything else. But this is a wild speculation. And a lot of physicists are right now trying to understand how could you form such a thing naturally. Yes, please.
So I love the Oumuamua simulation. I realized it showed that the trajectory was simply distorted as it passed through the sun.
Yes, so it came in like this, and then the sun turned it around and it was distorted.
That's my question. Is the
No, it is proven that it is not connected to the sun. If it would be, or some other gravitational field, no. No, it is actually its velocity is roughly the same velocity of all the stars that are moving around us. So you know that the sun is moving around the galaxy with roughly 200 kilometers per second. The next star is also moving with 200 kilometers per second, and the differential velocity is actually what we see with the star. So the Oumuamua is basically bound to the galactic center, but it is circling around the galactic center, and it is kind of wandering from star to star.
But it's not passing through as a wanderer.
Through our galaxy. No, only through the solar system. It is still bound to the galaxy.
And the second question was, what's the thing?
Yes.
What is the thinking in terms of expansion? The string theorists would say, oh, it must be expanding in 11 dimensions. And what is the thinking as to how many dimensions of expansion there are?
So first, you mentioned the string theory. It has the beauty that it has 11 dimensions, but 7 of those 11 dimensions are actually rolled up in infinitesimally small units so that we can't really see them. Only if we have a super microscope or some collider, we would be able to see these other dimensions. So then there are 4 dimensions left, which is space and time. And the problem is the curvature of space, which mass is creating, is very hard to imagine. Right? In 2 dimensions, you can think of a space like a flat piece of paper. And then when you put a ball in there, which is a heavy mass, then that is kind of like a trampoline or so. It is a curving space. And when you take another ball and you run it around the trampoline, then you will find that that ball will actually rotate around the big mass. Also, there are no forces acting between the big mass and the other mass. So the curvature of space is what gravity is of. And it's very hard to imagine a 4-dimensional space curvature only if you take time into account. And if you squeeze time and space together, you get this 4-dimensional curve. So I think in this picture, everything is still fully consistent with Einstein's theory of relativity. But the quantum nature of the universe, I mean, that's the big drama that we have since about 50 years or so. Einstein, until his end of his life, tried to combine quantum physics and relativity. And they just don't fit together. They don't, there's no common denominator of those 2 theories. Okay, last question.
On the kilonova discovery in August, I listened to a clip from one of the scientists that were working on it. They confirmed that the speed of gravitational waves is the same as the speed of light.
Yes.
I wonder if you would just expand on that.
Yes. So in this movie, you heard that this chirp, this which was basically the faster and faster rotation of the neutron star, came about 1.7 seconds before a gamma ray burst that basically showed that something was exploding there. And that sets a very strict time limit because the gravitational waves are producing that chirp, which we hear, and the gamma ray burst is producing the light. And it's the same thing like, for instance, in the early 1920s when movies all of a sudden were done with sound. You got the sound into the movie. That is the first event where we basically have a movie of the sky, and we also have the sound. And the fact that they are synchronized with each other means that the speed of sound and light must be the same. The speed of actually gravitational sound and light must be the same within a very, very small precision, because you have to imagine this object, the light, was on its way for 170 million years, and the difference was just 1.7 seconds. So this is it's an extreme high precision, the same velocity. And the reason why the light came a little bit later than the sound could also be the physics of the explosion. So for instance, the light we only see when it is shining towards us, and when you imagine the light coming out of a funnel and then being accelerated, then it could have taken a little while until it shines in our direction. So all of that is consistent with basically exactly the same speed between gravitational waves and sound and light. Okay, I thank you very, very much. It was a wonderful experience. A great pleasure, and I will look back to Hawaii and also to this event this evening with great pride. Thank you. Adios.